welcome back. So, we will continue with our discussion on Voronoi diagrams and the related dual called Delaunay triangulation. So, in the last lecture, Professor Agarwal discussed about the, the relationship between convex hulls and Voronoi diagrams, and there is also a close connection with the Delaunay triangulation, namely that if you look at the paraboloid transform, you take a set of points on the plane and you lift them to the paraboloid, let us say from the two-dimensional plane to the three-dimensional space onto the paraboloid, and you so the points are projected vertically onto the paraboloid. Now, when you construct the convex hull of the points on the paraboloid, and when you project it back to the two-dimensional space, essentially what you get is a Delaunay triangulation. Okay. So, this fact was established in the last lecture. So, this is of course one method of constructing Delaunay triangulation, that is reduce the problem of the 2D Delaunay triangulation or Voronoi diagrams to that of constructing a convex hull in the 3 dimensions. However, for reasons that probably is somewhat beyond the scope of these lectures in this course, it actually is better, or let us say more stable, to construct the Delaunay triangulation directly. And the basic intuition is the following, that when you are constructing a Voronoi diagram or even the three-dimensional convex hull, you are dealing with dealing with higher degree curves in the sense that when you're trying to construct Voronoi diagrams, you're looking at the perpendicular bisectors of 2 points. Okay, so that itself is a higher degree. It's a line, but it still depends on the coordinates of the 2 points. Whereas the Delaunay triangulation, okay, directly connects the points by edges, right. So, for instance, if I have these points and my Delaunay triangulation, my Voronoi diagram looks something like this. Okay. The Delaunay triangulation is actually, it connects the points directly, right. So, here is a Delaunay triangle, okay. Here is the other Delaunay triangle. Okay. So, we are not defining these red lines are defined on the basis of, let us say, these given points A, B, C, D, but the red lines are the perpendicular bisectors of the segment joining A, B, and so on and so forth. So, the equation of this red line depends on these 2 coordinates, whereas the Delaunay triangulation edges are directly obtained by the line segment between A and B. Okay. So, numerically, when you actually implement these algorithms, it is easier to handle rounding errors, etc., when you construct a Delaunay triangulation directly rather than Voronoi diagrams. Okay. So, we will today discuss actually some direct methods of constructing Delaunay triangulation. So, Delaunay triangulation, of course, is the dual. I mean, one way of defining is that Delaunay triangulation is the dual of the Voronoi diagram. We will be restricting our discussion to 2 dimensions, okay, but even in higher dimensions, okay, there are analogous relationship between Voronoi diagrams and Delaunay triangulations. So, one very important or key property of Delaunay triangulation is that when you look at, let us say, this triangle constructed by the blue line segments, if you look at the disk or the circle or the circumcircle of the triangles of the Delaunay triangulation, namely okay. So, this is the circumcircle of the triangle ABD. Okay. And similarly, you can draw the circumcircle of the triangle DBC, and it will look something like, well, so I am drawing without compasses, so you will have to believe what I am drawing. But one thing you will notice, of course, this is only a small diagram of 4 points, is that the circumcircle of ABD does not contain the point C. Okay. And likewise, the circumcircle of DBC does not contain the point A. In other words, these two circles, define discs which are called Delaunay discs. Okay. So, Delaunay discs basically are defined as the interior of the circle of a Delaunay triangle. Okay. So, these Delaunay discs have this very nice property, and which probably is not very intuitive at the first sight, is that they are empty. Okay. So, Delaunay discs, so the Delaunay discs, say D, okay, intersection with the set of points S, okay, is empty if you do not consider the points on the boundary. Okay. The points that define the disk. So, this is a very nice property that the Delaunay triangulation gives, and this is not true for an arbitrary triangulation. For instance, we can construct this example. So, take again 4 points. Okay. Consider this triangulation. Okay. A, B, C, D. Let me draw the circumcircle of ABD. Okay. And certainly this circumcircle or this disc, okay, it cannot qualify, or it is not eligible to a Delaunay disc, because the point C is contained within the circumcircle of ABD. Okay. So, this is not a Delaunay triangulation. Okay. Therefore, it is not even obvious that that Delaunay triangulations would exist. But on the other hand, if you look at the construction of a Voronoi diagram, and since Delaunay triangulation is the dual of the Voronoi diagram, this is an indirect proof that Delaunay triangulations exist. But if one were to simply go about it directly, in the sense that prove that there exists a triangulation such that the circumcircle of every triangle is empty, proving this property or proving that such a triangulation exists would be extremely non-trivial task. Okay. But let's try to sort of at least sketch a kind of an intuitive proof of why such a triangulation exists. Now, if you consider these 4 points A, B, C, D, of course, this A, B, C, the circumcircle of ABD is not a Delaunay disk because it is not empty, but instead of A, B, C, D, if I did not draw this triangle, okay, and decided that I should draw this diagonal. Instead of BD, let me draw the diagonal AC. Okay. And therefore, even my circumcircle has to be redefined. All right. So, let me try to draw the circumcircle now. And at least a freehand drawing should be convincing that none of these two circumcircle contain any other point, okay, namely that these two are empty. Okay. The circumcircle of ABC and the circumcircle of ACD, both of them are empty, and therefore, by definition they are, they qualify to be Delaunay discs. And so this triangulation, does meet the condition of a Delaunay triangulation, right. Is this a coincidence? Okay, not really. So what's really happening is that if I take 4 points, okay, 4 points in convex position, so you can see that, okay, so I have these 4 points, arbitrary 4 points in convex position. Okay, we can prove rigorously that either, this drawing this diagonal will be consistent with Delaunay triangulation, or if this is not consistent with Delaunay triangulation, that is the circumcircle is not empty, then certainly the other one will be. Okay. So, one of these two diagonals, okay, must satisfy the property of the empty disk. And why is it so? And why is it so? Well, if you think about it, the underlying property is that if the 4 points, lie on a circle, okay, so if I take a circle, okay, and put 4 points on it, right. So from our knowledge of high school geometry, right, let's call these angles alpha, beta, gamma, delta. Okay. We know that the sum of the opposite angles when all the vertices are on the circle, they are supplementary, right. So, alpha plus gamma equal to pi, and delta plus beta is also equal to pi. Okay. Of course, from our assumption that we made in the case of Voronoi diagrams of point sets, and the same thing holds for Delaunay triangulation also, we assume actually that no 4 points are co-circular, that is the points are in general position. Okay. So, one of the assumptions that we make when we design an algorithm for Voronoi diagram is that no 4 points are co-circular, that is the points are in general position. So, the point set S does not have 4 co-circular points. So, therefore, this kind of configuration cannot exist. Okay. This kind of configuration, it is also called the general position assumption. Now, the general position assumption is not necessary, but it is very useful actually to simplify many of the proofs and even simplify some of the special cases that arises when we have to deal with 4 points in a circle. It does not really change the asymptotic complexity, it does not change the basic properties of Voronoi diagram, but it does have some bearing on some extra cases that one has to handle. Okay. So, it is convenient to make this assumption, okay, and let us not make life harder by doing away with this convenience. So, when this kind of configuration cannot arise, essentially what we are saying is that either, so we have the situation that all 4 points can't be on the circle. Okay. So, either they will be it will be inside, okay, like this, okay, in which case you can see that when you consider the Delaunay circle, or sorry, the circumcircle of, if I drew this diagonal BD, okay, then the circumcircle of this diagonal, okay, would definitely contain, C has come inside now, okay, contains C, and therefore this diagonal cannot define the Delaunay triangulation, okay. And since we pulled the point inside, okay, again by our knowledge of high school plane geometry, we have actually now done the following. We have now alpha plus gamma, okay, is strictly greater than pi, and delta plus beta is strictly less than pi. Right? So this is the situation. So if we drew the diagonal BD, then this is the situation, and this basically corresponds to the to the case where this is not a Delaunay triangulation. Okay, that is, we have drawn the diagonal DB, and the angles lying on the opposite side of the diagonal, okay, exceeds pi. Okay, and since this exceeds pi, the other pair of diagonal angles delta plus beta is actually less than pi, and therefore if we had drawn this one instead of this diagonal, we had drawn this diagonal. Then by the fact that delta plus beta is less than pi, okay, now if we draw this circumcircle, okay, this is no longer a circumcircle because it does not go through 3 points of the triangle. Okay, so I have to redefine my circumcircle, and because delta plus beta is less than pi, when you draw the circumcircles, by the property of again the supplementary, the sum of the supplementary angles, this point, because delta plus beta is less than pi, B is going to lie outside of the circumcircle, and likewise when you draw the other circumcircle, same thing with the same property. Okay, it's getting a little cluttered, but I think you get the point. So because the sum of delta plus beta is less than pi, the point D must lie outside the circumcircle of ABC, and similarly the point B is going to lie outside the circumcircle of DAC. Okay. So this is a very basic property, and that will be the basis for a very simple algorithm. Okay. Namely, let us say that we want to construct a Delaunay triangulation. So a simple algorithm for Delaunay triangulation would do the following. Would simply so this, drawing the diagonal AC instead of drawing the diagonal DB, this can be thought about as flipping the diagonal. Okay, so this operation is called flipping the diagonal. So we take two triangles that share an edge, okay, and if the two triangles do not meet the specification of a Delaunay disk, that is the disk is not empty, then we flip the diagonal. Okay, so we from this situation, okay, we go on to the other situation. Okay, so this is basically flipping, edge flipping. Okay, and this edge flipping is used as a basis for constructing, can be used as a basis for constructing Delaunay triangulation. So what do? We start with some arbitrary triangulation. Right. notice that an arbitrary triangulation using some of the methods that we have learned in the course, okay, will contain about 2 n minus 2 minus k triangles, okay, where k is the number of points on the convex hull of S. Okay. So, in other words, we only triangulate the interior of the convex hull. So, if the given points are like this, okay, this is the convex hull. Okay. So, we are only going to construct the triangulation interior to the convex hull. Okay. So, whatever triangulation you construct, some arbitrary triangulation. These are the points in the boundary, the k points in the boundary. If the k points in the boundary, then the total number of triangles are defined by can be, you can verify this is 2 n minus 2 minus k. Anyway, it is still linear. Okay, the number of triangles is always going to be linear in the number of points. Okay. So, we start with an arbitrary triangulation, and then we do the following. We examine pair of triangles that share an edge. Okay. So, these two triangles share an edge, okay, T1 and T2. Now, what we check is that does the Delaunay disk of T1, let us call it d of T1, okay, does d of T1, which contain the point of T2 lying on the other side of the common edge, right, on the opposite side of common edge. Call it E if you will. Okay. So, if this contains the point of it contains the point on the other side of the common edge, then clearly this is not a Delaunay disk, and therefore, we must flip the diagonal. Okay. So, then this must basically be changed to this situation. Okay. So, T1 and T2 will disappear, and instead they will be replaced with, let us say, T4 and T5. And T4 and T5, as we have just observed, will necessarily satisfy the property of Delaunay disk. Okay. So, we have fixed, you know, the problem with just a pair of triangles sharing an edge, and we keep continuing on this. Okay. When so T4 and T5 are legal. Okay. So, T4 and T5 are legal in the sense that, you know, their Delaunay disks do not contain the point on the other side of the edge, are legal. Okay. Or you can say the diagonal itself is legal. Okay. And now we check if there exists another pair of triangles that are not legal. Okay. So, we keep doing this till we come to a situation where there are no more that's all the diagonals are legal. Okay, until all diagonals are legal. Okay. So, we just keep continuing doing this thing. Of course, it looks like a very unstructured process where, you know, we are just picking up, looking at some edge, looking at the two triangles that share that edge, and just verifying, okay, using some coordinate geometry, whether or not the two disks are legal Delaunay disks. Okay? If they are, then we leave them if as it is. If they are not, then we move on to another edge, look at the pair of triangles sharing that edge, and so on and so forth. So, first of all, it is not even clear that this is going to converge. Why is it necessary that that the edge once flipped does not get flipped back? If it does not get flipped back, then of course it will converge. But what is the proof, or what is the argument that an edge once flipped will not get flipped back? Okay. So, for that we will make a few observations. I will not give you a very rigorous proof, but something that can be refined to a proof. Okay. So, one thing to notice, again, this is a very important property of Delaunay triangulation. Okay. Let us go back to the okay, let's draw another figure. Okay. So, consider again some 4 points. Look at the two diagonals. Okay. A, B, C, D, and the So, suppose that BD is the legal edge. Suppose BD is the legal edge. Right. Now, consider this angle alpha. Okay. So, this is a legal edge. You draw the circumcircle. C should be outside of the circumcircle. Right. Look at this angle alpha prime. Alpha prime. Okay. How do you compare alpha and alpha prime? Okay, if C was actually on the circle, okay, if C were on the circle, then alpha would have been equal to alpha prime, right? So, if C was on the circle, then again from your knowledge of plane geometry, that these are angles angles on the same arc, okay, lying on the circle. Suppose it were like this. So, what I am saying is, suppose C was somewhere here, okay. So, then this angle would have been equal to alpha, okay, because they subtend on the same arc, okay. But C is actually outside, okay. So, C is actually going to be smaller, okay. So, the angle alpha prime alpha prime is strictly smaller than alpha, okay. And suppose alpha was the smallest angle in triangle ABD, okay. Suppose so we can do more case analysis. Suppose in one case it is such that the triangle is such that alpha is the smallest angle in triangle ABD, okay. What it implies, okay, is that if we had used the diagonal AC instead of BD, okay, if we had used the diagonal AC instead of BD, then alpha prime would have been one of the angles of the two triangles defined by the diagonal AC. Notice that AC is not a legal edge, okay, because we have said BD is the legal edge, and so if you try to draw the circumcircle of ADC, it's going to contain B, okay. So, given that BD is the legal edge and alpha is larger than alpha prime, it implies, okay, that the smallest angle of the triangles the two triangles defined by this legal edge, okay, the smallest angle of the triangulation defined by the legal edge, legal as in sense of Delaunay triangulation, okay, is larger than the smallest angle of the triangulation defined by the illegal edge. Okay. And this observation can actually be formalized into some kind of a proof which says the following, that as we flip the diagonals, okay, when we continue flipping the diagonals, depending on whether it is legal or not, okay, the minimum angle of the triangulation increases. Okay. In fact, Delaunay triangulation okay, maximizes the minimum angle of the triangles among all triangulations. Okay. So, this is another very important property of Delaunay triangulation, that when you actually do the edge flipping, you are going to increase the minimum angle. Okay. So, every time you do edge flip, okay, the minimum angle of the triangulation is increasing, and therefore, okay, this is another proof, or this is another property because of which this procedure converges. Okay, the edge flipping actually converges, okay? But it still does not tell you, how long it takes. Okay. Now, for that we will go back to the lifting transform. Okay. So, what the lifting transform does, okay, so let me try to draw a picture. So, we have these two possible edges. So, so here is the paraboloid, okay, and it has to be, well, I mean, it is actually a three-dimensional paraboloid, but I can't draw that picture very well. So, when you are projecting onto it the points, just look at the 4 points. Okay. So, we saw in the last lecture that the circle defined by a triangle here, okay, or the disc, okay, is when you project it to the paraboloid, okay, if the circumcircle corresponds to a Delaunay triangle, okay, then all other points, okay, will be to one side of it. Okay. So, that is what actually how why there is this nice mapping between the three-dimensional convex hull. So, the 3 points actually turn out to be the face of a convex hull in the 3 dimension, okay, and therefore, all the points has to be on one side of it, and therefore, the Delaunay disk, okay, if this point lies outside of this circle, okay, which is a property of the Delaunay disk, then this point is going to be on the other side, okay, whereas if it is the other way around, okay, that is, if it is like this, okay, then this disk, okay, will contain this point, and when you project this circle onto onto the paraboloid, okay, this point is actually going to lie below the face. Okay. To make it more clear, you know it's like this. In one case, if this is, so now I have to draw some kind of a three-dimensional picture. Okay, in one case, the triangle is going to fold like this. Okay, so A, B, C, D. Okay, so this face, okay, or the circumcircle passing through this face, okay, this point will lie below it. Okay, so it kind of folds in this way. Okay, it kind of folds in this way. But if you drew the other diagonal, okay, then it's going to fold in the other way. Okay, so these 4 points, okay, are going to lie on the parabola, okay, and it's going to fold like this. So it will be convex as opposed to concave. Okay, so the legal diagonal actually folds it in the convex position, whereas the other diagonal folds it in the opposite direction. So you can see that as you basically flip the diagonal, okay, the diagonals are actually kind of coming down. Okay, so your triangles are getting closer and closer. The face of the convex, well, it's not yet not convex, but basically the triangles are getting closer and closer to the surface of the paraboloid, right? And so, and the diagonal, once it comes below, it's never going to rise up again, right? Because this is an illegal diagonal. Okay, so you cannot again raise the diagonal, because the diagonals, all the points should come actually. It should be basically, this point has come below the diagonal. Okay, so if I raise the diagonal again, the point is going to fall below, right? So a diagonal, once it falls below, okay, it's never going to rise again. Okay, and therefore this is also an analysis of the how many times how many diagonals can be flipped. Since a diagonal cannot be flipped more than once, okay, the convergence takes order n square flips. Okay. Now this is of course modulo data structure. Okay. So you have to use some clever data structure so that the overall running time becomes about n square. Okay. So we have only given a proof that the total number of edge flips is n square. Okay, n square edge flips. So using appropriate data structures. You can obtain order n square running time. The good thing about this is that it's a very simple algorithm, but it's n square, whereas you know that a three-dimensional convex hull can be constructed in n log n time, which means that a Voronoi diagram can be constructed in n square time, n log n time, and therefore a good algorithm for Delaunay triangulation should not take more than n log n time. Okay? Whereas this one, although simple, takes n square time. Okay? There's another observation, okay, which is also kind of important, that if you are given a arbitrary triangulation, okay, how quickly can you verify that it is a Delaunay triangulation? It may or may not be, but so your job is that I give you a triangulation, okay, where every face is a triangle connecting the points, given set of points, and now your job is to find out if this triangulation is a Delaunay triangulation. Okay. So you can go back to the original definition, basically, that you look at the circumcircle of every triangle, okay, that's a disk, and just find out if the disk contains any other point. Now if you do that, you have about order n triangles. Okay. So if you do this for every triangle, then order n triangles, okay, and then you have to check with respect to every other point, right? There are n points. So that means that check if any point lies within the disk. Okay. So again, using some let us say appropriate analytical coordinate geometry formula, you can do the test for every point in constant time, which means that for every triangle it will take about order n time to find out if it is really empty or not, and there are n triangles, okay, which means that it again going to be an n square is going to be an n square procedure, right. What I have defined is basically a theta n square procedure. But there is a very nice property that says the following, that if I can verify, okay, if we can verify for every edge that the two triangles sharing the edge are legal, then it is a Delaunay triangulation, right? Which basically means that I am doing only local checks. Okay, I am looking at the triangulation. I am not trying to check with respect to every point. Okay, there is some triangulation. I am not going to take every circumcircle and check with respect to every point, but I will only look at an edge, okay, look at the two triangles sharing the edge, draw the circumcircle. Okay. If this circumcircle does not contain this point and this circumcircle does not contain the point, and this holds for every such pair of triangles, then it is a Delaunay triangulation. In other words, what I am saying, this is called a local Delaunay property. So, I do not need to check with respect to all other points whether they are contained inside, okay. Local Delaunay property. So, and local Delaunay property, okay, implies the global property. Okay. So, that is a very nice result. Okay. The proof is by contradiction. I am not going to do this. Basically, what you can show is that suppose there is some Delaunay triangulation there is some triangulation that satisfies the local Delaunay property, okay, and suppose there is some violation in the sense that although it satisfies the local property, there is some point that lies within on the disk, then you can actually work backwards to show that it will violate some local property. Okay. So, I am not going to go into a strict proof of this, but it can be worked on the basis of contradiction. Okay. So, this is the some of these nice properties about Delaunay triangulation. And by the way, the minimum angle property is very useful for all kinds of modeling. Okay. So, if you have only the points of the surface, okay, and you want to actually reconstruct the surface, it is usually very useful to do the triangulation of those points so as to minimize the minimum angle. Maximize the minimum angle. Okay. So, this is used all the time, and therefore, the Delaunay triangulation the most popular kind of triangulation when you are doing surface reconstruction. Okay. Okay, but then again let's go back to this problem of efficiency. Okay. So, this simple algorithm gives you an n square kind of running time. Okay. How about if I desire a better running time? In other words, can I match the n log n running time using a direct approach rather than going through the lifting transform and building the 3-dimensional convex hull? Can I directly construct a Delaunay triangulation in log n time? And there is actually a very clever or simple method based on a very general scheme called randomized incremental construction, which is also going to be one of the lecture topics in near future. But I will just give you a very brief description of that randomized incremental construction. Okay. What you do is you begin with an arbitrary triangulation. Well, actually, don't even. So just start with a set of points. Okay. Okay. So given the set of points S equal to P1, P2, Pn. These are all two-dimensional points. Do the following. First, generate a random permutation of S. Okay, say call it Q. Okay, and that now consists of a random permutation of the given set of points. Call them Q1, Q2, Qn. Enclose the points in some large triangle, okay, and then pretend that you are adding these points in the sequence of Q, that is Q1, Q2 up to Qn, and whenever you add a point, okay, you should inductively maintain the Delaunay triangulation property. Right. So, suppose I have so far added these 3 points. Right. So, suppose these are the first 3 points to be added, and well, these are some artificial points, the actual points are all inside. Okay. And with one triangle, of course, there is nothing to really be worried about, because these points don't exist actually. They are going to be added one after the other. So, the first point that add is Q1, let us say Q1. Okay. When I add a point, then my the first thing I do is, add some edges so as to make it a triangulation. Okay. So, I add these edges. Right. So, now this triangulation consists of these artificial points A, B, C and the first point Q1. Right. Well, I mean, in this case there is nothing to worry about, because if you draw the circumcircles, okay, they will not contain any of the points that have not been added. The other points actually don't exist. They are in some queue to be added in future. Okay, but if I draw the circumcircle of this, okay, certainly it's not going to contain A and vice versa. Okay, so this can be verified. So right now there is nothing to worry about. Okay. So as we go on, we keep on adding the next point, okay, and inductively maintain a Delaunay triangulation of the points that we have added so far. Okay. So at some point we may have, the diagram may look like this. Maybe these are the points added, already added, and this defines the Delaunay triangulation, and these are the points that have not been added yet. The next point to be added may be lying in here. Okay. So what we do is, okay, let me draw a few more edges. Okay. So suppose this is the next point to be added, then we do exactly what I said before. We first draw these edges, but now there is a problem, that if I draw this circumcircle, okay, it may contain some other point, like it contains this point. Okay. So in that case, what I am going to do is I will try to restore the Delaunay property by flipping this edge. So this edge will be flipped. This is the new point to be added. Okay. So I flip this edge, I get this. Okay. Now I have these two new triangles. Okay. Now, once we have the new triangles, okay, you may have again, if you look at the circumcircle of this, okay, it may again contain this and this may be violated. So, I may have maybe forced to erase this and add this. Okay. So, this process is going to go on, okay, till my triangulation becomes legal. Okay. And notice that every time I flip a diagonal, okay, one of the endpoints of diagonal is the new point, because if you do not consider the new point, the previous triangles were all legal. Okay. So, it must, if it violates something, it must include the new point. Okay. So, in other words, all the triangles that we are going to add because of this, okay, if this is the new point, if this is the new point, then all the new triangles basically will have their apex in this. Okay. So, this is the new point, maybe this was qi that was added. So, depending on the degree of this point, you will have to be basically doing that many edge flips. Okay. The number of edge flips will be equal to the degree of qi once we have actually completed legalizing this. That is, now up to from q1 to qi, this is a legal Voronoi triangulation, legal Delaunay triangulation, and this process goes on. Then next we add qi plus 1 and repeat the process. Okay. So, at every step when we add the next point, there is some work to be done depending on what is the final degree of the point. Clearly, the degree of a point can be n. So, in the worst case, we may be doing about order n work per iteration, which means that to add all the n points, we will be doing about n square work. Okay. But this is not the right way of analyzing this kind of algorithm. That is why I said this randomized incremental construction is a technique where we actually take advantage of the fact that it is not an arbitrary, it is not a worst case sequence of point, but somehow the point that is to be added next, okay, there is some kind of averaging argument. The averaging argument is you can see it as follows. We will actually, as I said in the later lectures, we will formalize these whole arguments, that you look at the Voronoi diagram that contains qi. Okay, a Delaunay triangulation. A Delaunay triangulation is after all a planar graph, and in a planar graph, the degree of a vertex, okay, is constant. The average degree of a vertex is constant, and therefore, when you add these points in a random order, the expected degree of qi, the expected degree of qi is constant, order 1, and therefore, the number of edge flips that you do, the expected number of edge flips that you do in a iteration is constant. Okay. So, that is one of the things. The other thing is that whenever we also need to worry about the points that lie within the triangle. When I picked up qi, okay, I should know that qi lies in a certain triangle. Okay. So, I also have to maintain the triangulation. Okay. So, there is the other job of maintaining the triangulation, so that when I add a new triangle, so whenever there is a new triangle, so whenever I add a new edge, the points have to be redistributed. Okay. So, I am always going to keep track of which point lies in which triangle. Okay. So, I will maintain a kind of a bipartite graph where these are the points not added yet, okay, and these are the current triangles of the Delaunay triangulation, the current triangles of the current Delaunay triangulation. Okay. And a point, I can draw an edge between a point and a triangle if the point is contained within this triangle. So, of course, a triangle could contain many points, okay, and as you refine the Delaunay triangulation, this graph is going to change, and the amount of change that will happen in the graph, again you can bound it. Of course, it requires some proof that the amount of change that happens in the graph is expected to be about well, it is not quite constant or log n. Over the entire sequence of this insertion, it is going to be about n log n, and that gives the order n log n running time of this incremental construction. Okay. So, to summarize, okay, so claim the randomized incremental construction for Delaunay triangulation takes expected order n log n time for any arbitrary set of points. That is very important. Okay. We are not averaging over the set of points, we are only averaging over the sequence of insertions. Of course, a particular insertion sequence can be bad, but when we average over all possible insertion sequences, and that is why we choose a random permutation, then the expected running time is only n log n, which is as good as doing the lifting transform or doing any other algorithm, because this also happens to be the optimal time for constructing Delaunay triangulation for any arbitrary set of endpoints. Okay. So what we basically looked at today was we looked at some very basic properties of Delaunay triangulation that was useful to actually define the notion of Delaunay triangulation, as well as also come up with some preliminary but not very efficient algorithms for Delaunay triangulation, namely the edge flip algorithm. And then we looked at another algorithm, namely the randomized incremental construction, which leads to an optimal n log n algorithm where you maintain the Delaunay triangulation inductively by adding one point after the other, and the addition of the points is not done in some given sequence, but you actually permute the initial sequence. So you add them in a random sequence, and then you can prove that the expected running time of this procedure is n log n. So that's all for today.